0. Yeah, it goes to we can say that the system is exponentially stable or asymptotically stable. Okay, so actually this is from the lemma. The proof is quite lengthy, so but actually we just follow by omitting one term. Okay, so we propose this one. Yeah, we call it as the boundedness lemma. In here we are just we assume that in this term actually with this condition, then the solution is like this. Yeah, we can see that solution is goes to 0 also, and it is also exponentially and asymptotically stable. And actually the proof is quite lengthy, so I made a sketch of the proof only. Actually this is characteristic equation given is as this, and then in order to be stable, the eigenvalue has to be negative, or lambda has to be negative, and we can use the Coulomb contradiction by setting tau delta greater than 0, and finally we can by using the Coulomb contradiction, the result is the system contradicts this one, so the system has to be stable. Okay, and also the boundedness can be given as this. Okay, so also we have the direct consequence of the previous one, known as the Lyapunov-Krasovsky-Lies theorem. This is theorem that actually is not appear in the paper, not yet appear. Okay, so if this one is fulfilled, then the system is not just exponentially stable, but also globally exponentially stable. Okay, so if the proof is from the direct differentiation from the previous one, then we can take the x here. We can see that x is bounded. There is a free here, so the x goes to 0 as time goes to 0. Okay, so this is our main theorem. Assume that we are using the static controller, just a static. This is not the adaptive one. Okay, and we apply this one to the previous one, the system with the non-zero free here. Okay, then we can prove that the system is controllable. Based on the work of Quant in 1980. Okay, and this is the theorem. Then if AB is controllable, then there exists K that stabilize 2. Okay, so the proof quite lengthy, so we give but this proof can be seen in the paper. It's quite maybe most of our paper is for this proof alone. Okay, so we said here as this one as to the transform of variable, change of variable, and then we arrive at this one, and by reordering we can get this one. Actually the triangle here, it can be less or equal or bigger than equal. Yeah, we can set this, and finally we can make a term by term comparison in order to get that the k to k1 to kn always exists. So the k are always exists. And then we come to the numerical simulation. Actually, I got this from Monje. Actually they propose fractional order controller. They use and this is actually they plan as simple as this one, but in Monje L here is just only one minus s. In our work we are going to work with a very long delay, so we set L to minus 50. Okay, actually the system is stable, so it's like this. But it's very slow. But in order to increase the speed of the system, we use the reduction method. This is so we change the previous one into the space form, and we get this one actually z. And finally, we get the last one. This one. This is not a delay-free system because of this one. We have u here. But we can use from the proof of the theorem. This one actually the last equation from the sketch with the gamma. These two one, this and this. Then we can choose k. Such that actually from this one we can choose k has to be like this. K has to be set from minus 0, 0, 4 to 0. Okay. If k is set we set k here to minus 0.002, and we can get the result. We can see that the system are stable. And okay, one more. We change L from 0. This one is if we change L from 0 to minus 50. While the next one, if we change 0 more than 50 actually. So from 0 to minus 100 seconds, the delay. And we can see the system is still stable. This one is not quite good in terms of the response. Okay, so finally we come to conclusion. So we have proved the robustness property of the system, and then we can see that if the gain k is small, in the example we see that it's from minus 0.004 to 0, the system will be stable. And then also the result is proven to be bounded or to be remain stable in the wide region of input delay. Okay, so that's all.